Okay, today we are going to cover chapter 10 from the textbook, and we are going to see new data structures like interval trees, segment trees, and priority search trees. I'm going to first summarize the problem that we are going to solve and also give an overview of the data structures we are going to learn. Then we are going to go into the details of these data structures. So we have seen earlier, window queries, orthogonal range queries in chapter 5. If you remember, the problem in chapter 5 was we have a bunch of 2D points, actually a lot of them, okay, which prevents the number of these points prevent us to do linear searching. So we don't want to do linear search all the time. We want to have sublinear search algorithms. And our query, the query that we perform is an orthogonal range query where we have a window and our goal is to figure out which points are in this window. Okay, so that was the problem in chapter 5. We have a bunch of points and for example, build an index structure on those, like 2D range trees or KD trees, which help us to solve this windowing queries, orthogonal range searching queries in sublinear time. When we use range queries, 2D range trees, with fractional cascading, we can solve this in log n plus k time, or log n plus k time. And if we use KD trees, it was O square root of n k times. So these are the worst case complexities in the case of 2D range tree, and this is the case for KD tree. The disadvantage of KD tree was the running time. It's worse than O log n. And the disadvantage of 2D range trees is its space complexity. While KD trees require this much space, O(n) space, we need to have O(n) log n space for range trees. So that's the added cost of using 2D range trees. In addition, in order to get to this log n from log square n, in order to reduce this 2 to log n, we need to use a complicated algorithm named fractional cascading. And in order to implement that, we cannot have a regular 1D range tree. We need to have an array-based implementation, set up these pointers from the supersets to the subsets. So this was what we did in chapter 5. So today's topic, chapter 10, is similar to this in terms of queries. We are going to have again windowing queries in which we are going to have rectangles with axis parallel rectangles, but our input is going to be different. We are going to be our input is not going to be a set of points, but they're going to be a set of line segments. All right, so we will be given a set of line segments, and we are going to look at different versions of this problem. Okay, so for example, these may be our line segments. Like this, I connect these 2 points. And we are going to assume that the line segments do not intersect with each other. They may touch at the endpoints, but we will assume that they're non-intersecting, because intersecting line segments will introduce new problems that is going to increase our computational complexity, especially in the case of the segment trees problem. So imagine we have, so only this one is left alone, I think, or maybe, yeah. So we are given a bunch of line segments like this. So this is the most general version of the problem we are going to solve. Given these line segments and given a query window, our goal again will be to develop sublinear algorithms. We can do which line segments intersect with this in O(n) time easily by going over all the line segments and checking it with respect to this window. But we don't want an O(n) algorithm, okay? With these windowing queries, our goal again is to do this very fast. If the number of line segments is huge, under order of millions, and we want to do a windowing query, we need to be able to do it fast. So that's the purpose of this chapter. Avoid exhaustive search of all of your line segments against your query. Try to do something in sublinear time, and both of the algorithms that we are going to see today, they are going to provide us O log square m plus k time complexity. This is going to be the query search complexity against the window that we have. Okay, but we're going to see different versions of this problem. So this, as I said, this is the most general version of the problem. In the first part of the chapter, we are going to see a more specific version of the problem in which the line segments are either horizontal or vertical. All right, not arbitrarily oriented like this. If these line segments are given to you as horizontal or vertical line segments, how can you solve that problem? We are going to see how interval trees can be used for this purpose. And in each of the cases, whether we use segment trees or interval trees, the actual interval tree or segment tree will be used to solve a one-dimensional problem first. So we are going to reduce this problem to several parts, just like the 2D range trees, for example. The main tree was searching on the x coordinate only, and the associated structures were assigned at each intermediate nodes, and they were 1D range trees on the y coordinates. So just like that, we are going to divide the problem into one-dimensional part first, and solving the one-dimensional case the second part is going to be the data structure that is needed, the associated structure that is needed to extend this to the 2D version. All right, but the original problem itself, in the most generic case, is like this. We have a bunch of arbitrarily oriented line segments. We have a window query, and our goal will be to figure out which line segments are contained, partially contained, intersects this bounding box. Okay, this query. Now, if you look at this problem, the first part of the chapter actually talks about why don't we just use the techniques that we have developed in chapter 5. For example, okay, these are line segments, but they have endpoints, right? A line segment has 2 endpoints. If I'm given n line segments, there are 2n endpoints. Why don't I build a 2D range tree or KD tree on these endpoints and use the endpoints to determine if, for example, if the endpoint of a line segment is inside this bounding box, it means that the line segment is partially inside. I mean, it may be the endpoint is maybe on the bounding box directly. Still, we're going to consider this as a line segment to output. Okay, so in order to output this line segment, a single endpoint being on the boundary is sufficient. So if we just query the endpoints of these line segments, we should be able to find all the line segments that intersect, right? Or no? Let me open the chat box. All right. So is this sufficient? Can we use chapter 5 directly to solve this problem? I mean, when I say, is it sufficient for the, I mean, is this true? If a line segment, maybe, is it an if and only if case? For example, if a line segment's endpoint is in the bounding, is in the query window, then the line segment should be reported as output. Okay, so this is the correct statement. But what about this? Is it an if and only if situation? I mean, in order to intersect a line segment, do we need to have both of its endpoints inside the bounding box? And obviously no, right? I mean, this is a very trivial question, and the example is right here. This is a line segment with both of the endpoints outside the query window, and we still intersect it. Okay, so this case here shows where the chapter 5 techniques will not work for this case. Okay, we cannot just have the endpoints and use these endpoints to determine whether we intersect or not. We need to have some other algorithms. By the way, this one looks like very much like the clipping techniques we have used in computer graphics, but we weren't interested in super efficient log square, I mean, sublinear query times against our clipping window. It's very similar to that, but here we were in computer graphics course, we were doing it in linear time. For every line, we were clipping it against this interval. Here, our goal is, given these line segments, build a data structure on them, which may take n log n time, because we are going to be performing on this data set. This may be like a GIS data set where these line segments are part of a roadmap. After we have the index structure, which we spend more than linear time, okay, in order to construct this index structure, we may spend more than linear time, which means that if you're going to make this windowing query only once, it doesn't make sense to use the techniques that we learned in chapter 10. I mean, if you just have one single query, just do linear search on them. That's the best, all right? But here, if this window query is going to be performed a lot, for example, again, it may be performed again millions of times, thousands of times, another query here, another query here. So if we are going to perform these queries a lot, then it makes sense to spend this one-time cost of index building and do the subsequent queries, which are a lot, in sublinear time. So that's the motivation behind these things. So what may be this? For example, it may be a map that certain GIS application providers provide their users, and the map may come with an index structure which is built by the application provider. And these queries may correspond to user queries, which may require instantaneous reply from the application. Therefore, imagine there are many users performing these queries simultaneously, that's when we need sublinear algorithms, okay? Just like the databases. So here today we have seen that, for example, just using the endpoints is not sufficient. But we will still use the techniques in chapter 5 to report the line segments which have one of their endpoints inside the query window. Okay, so this will also reduce the problem by making use of the techniques in chapter 5. We are going to focus on cases in which line segments do not have endpoints inside the bounding box. Okay, for that, we'll actually turn this problem into some other problem. We see that if a line segment does not have one of its endpoints inside, then it has to cross the boundaries, top boundary, bottom boundary, or right, left boundary. And if you look at the case of the first problem, where we have only horizontal or vertical line segments, the situation is going to look like this. So look at this figure in the book. These are all the possible, it shows a number of possible cases where horizontal and vertical line segments intersect our query window. And all of the ones that have, all of the line segments that have one endpoint inside or on the bounding box, on the query window, can be handled by using the techniques that we have developed in chapter 5. Okay, so we are going to then focus on only such cases. And in this example, only these two lines. There may be some horizontal lines as well that cross this one. But again, in the first problem, if we find a solution for only vertical lines, the same solution can be applied by changing the x and y coordinates to horizontal lines. Okay, so the way we approach this problem is we make observations, and every observation leads us to a more specific sub-problem, and we try to focus ourselves on the sub-problem. If we can solve the sub-problem efficiently, then we can solve the general problem later maybe. Also, we are going to even simplify the problem to a certain extent, and then we are going to get this, remove the simplification again, get back to the original problem, and we are going to see how we can achieve this, how we can extend the original algorithm. But the way we first try to find a solution to this problem is just try to simplify the cases, try to identify sub-problems. First of all, by observing that the techniques in chapter 5 can be used for line segments which have one endpoint in the query window, reduces the problem to cases like this, all right? Which means that for vertical line segments, for example, the line segment, in order to be reported as intersecting with the bounding box with the query window, as you can see, it has to cross both the top and bottom boundary. There is no case where it just crosses the top boundary only, and it intersects the query window. I mean, if it just intersects the top boundary, then one of the endpoints has to be inside the query window, whether it's partially overlapping or not. So if no endpoint is inside, and if this is a line segment that is to be reported, then the first observation we see is that it has to cross both the top and bottom boundary if this is a vertical line. If this is a horizontal line, we are going to make the statement for the left and right boundaries. If there's a horizontal line, which is going to be reported as intersecting with our query window, and this horizontal line has no endpoints inside the bounding box because we reported the ones with the endpoints already by using a 2D range tree. And therefore, in that case, the horizontal line segment has to cross both the left and right boundary. Why do we make this observation? To simplify our problem, actually. We don't need to check against both boundaries. If you're going to report a line, it's sufficient to just check against the left boundary. If a line segment intersects, I mean, if the left boundary is intersecting a line segment, then it's going to be reported for sure, okay? So because, as I said, when we make the observation, a line segment to be reported, it has to cross both of them. A line segment that has no endpoints within the bounding box, okay? So this is really important. All the observations we make, they follow some initial observations. So the statements that I make are only for certain line segments. For a vertical line segment that is to be reported and has no endpoints inside, it has to cross both top and bottom. So since it has to cross both top and bottom, just ignore one of them, okay? Ignore bottom. Just this turns into a problem that is like this, okay? We are so this is like the left boundary. Actually, the left boundary has some bounds. Let me show you a different figure somewhere here. We should have a figure that shows what the problem that we're trying to solve. I guess like this. So the problem that we try to solve turns into a problem like this. We are given a bunch of line segments. These are our segments identified by two endpoints, sx, xy, and s prime x and sy. If this is a horizontal line segment, again, when we simplify the sub-problem, we can just focus now on horizontal lines and horizontal lines that intersect with the left boundary. The left boundary is given with a specific x-coordinate is the same for the, it is a specific x-coordinate qx, and it spans the y-axis from qy to qy prime. So this is my left or right boundary, it doesn't matter, okay? So it's one of my vertical boundaries of my query window, and these are my horizontal line segments that I'm going to, in my database, that I'm going to index for, all right? So these are, so the problem now becomes, given a set of horizontal line segments and given a vertical boundary, like the vertical line segment, report the ones that are intersecting, report the horizontal line segments that intersect with this vertical line. So this is our problem, all right? Now, again, we will first start in order to develop a data structure for this. So this is a two-dimensional problem, as you can see, because we need to consider the y coordinates. This s here, although it's span on the x-axis, intersect with our query point, qx, it shouldn't be reported because its y coordinate is outside this qy prime range. So what do we do? The first, in order to develop this data structure, again, we just reduce the problem to a one-dimensional case by making some simplification. For example, let's try to first figure out what if this left boundary was an infinite line that extends all the way. Let's first find the horizontal line segments that intersect with QX only. This will turn this into a one-dimensional problem, which is like this. So the first data structure we are going to see, interval trees, are going to solve this one-dimensional problem. We are given a number of intervals on the x-axis. They actually, we are going to draw them as if they are, I mean, the book also shows them as if they are like, they have y coordinates also. But in the one-dimensional case, this is just for visualization purposes. We may have, this just shows that we may have overlapping intervals that span the x-axis. I'm just interested in their x boundaries, x and x prime. Okay, so this seems like I mean, in the original problem, they will have their y coordinates, so they will have some specific y coordinate, and we are going to check them against the left boundary. But here, what we are going to do is, in the first version of the problem, we are just going to assume we have a one-dimensional case. They're just on the x-axis. All right. Now you'll have a query. For example, our query QX, our left boundary or right boundary, will be a point query here. Okay. Now our goal will be to report which of these line segments, segment 1, segment 2, segment 3, which of them contain QX in their interior or at their endpoints. So endpoints are included. So if there's a line segment, for example, which just ends at QX, it should be reported. If there's another line segment which starts at QX, it should be reported, okay? Or other line segments which contain QX in their interior should be reported. So we have this problem now. We are given a bunch of intervals. These intervals are, they have left and right endpoints, and our goal will be to report which segments intersect QS. Okay, so this is the first problem, which is a one-dimensional problem. To solve this, we are going to use interval trees. Okay, so let's go ahead and introduce interval trees and how we can use that. The difficult thing is that, I mean, these line segments they have two associated endpoints, x and x prime, and this complicates the problem. We cannot just directly use binary search trees to solve this problem. This is not a one-dimensional range search problem because we have intervals, they may overlap, so we need specialized data structures to solve this problem. And interval trees are like this. Let me just now describe what kind of a data structure are interval trees that solve to solve this one-dimensional problem. Here is an example interval tree, and how actually the idea will be this. You're going to build a data structure like a balanced binary search tree in which the left and right subtrees contain at most half of the initial segments, the initial intervals we have. And we are going to partition the input intervals into 3 sets. Okay, these are partitions. They are, their intersection is empty set. The I left and I right, let me just describe these 2 sets first. I left are the set of intervals which are strictly to the left of some x coordinates. So this x mit is going to be our key value that we store in this intermediate node, okay, in this root node. This is going to be x mid. The x value will be our key, and the intervals that are strictly to the left of x mid are going to be the set of I left, which means that their endpoints, the right endpoints, if the right endpoint of a segment is less than x mid, it's a member of the set I left. If its left endpoint if the left endpoint of a segment is strictly greater than xmid, it's going to be a member of this I-right set. Okay, so if totally left and totally right segments are separated like this, and there will be segments which contain xmid either in their interior or at one of their endpoints. Okay, there may be a segment that start at xmid, and we are going to put those intervals into a set which we call imid. Okay, and imid, the intervals, the segments that appear in imid, they will never appear in left or right subtrees. So this is where they are stored, and that ends for it. So they don't go all the way to the leaf nodes. Okay, so here, this data structure is recursively built. For ileft, for example, I'm going to define another xmid, and this xmid is first chosen as the median of these 2n endpoints. I'm going to choose the median of those. I'm going to sort them first in O(n) log n time, and the middle one I'm going to designate as xmid. If out of these 2n endpoints I choose the nth smallest one as the xmid, there can be at most n over 2 line segments in ileft and at most n over 2 line segments in I-right. Okay, so which means that at every iteration, if I do this recursively, every iteration I'm going to be dividing my set into half or maybe even less, because there is a third set, which is this imid, which may contain also some of the line segments. All right, so it may even have, maybe it's expected, if we have some random line segments like this, its expected height may be less than log n. All right, or I mean, it will be asymptotically log n probably, maybe a constant factor smaller than log n, but still, just know that it's going to be a little bit shorter than a regular balanced binary search tree, because some of the intervals are just stored in the intermediate node, and they do not appear in the left and right subtrees. Okay, so now if I have a query, here is how the query is. So this is the idea of, this is an interval tree. And when I have a query, for example, if the query is to the right of xmid, imagine I have a query, let me just try to zoom in and put this in GIMP. Let me copy this region and just paste it in GIMP. Oops, didn't I copy it? Let me do that again. All right. Somehow the copying does not work. Anyway, I don't understand the Windows operating system all the time. So anyway, so we can actually take a look at here. I'll try to, I don't have drawing capabilities on this PDF viewer, but anyway, so imagine there's the QX. Imagine we have a query right at the X coordinate of this mouse pointer. All right, now you can immediately see that the line segments that are in I left, okay, cannot contain this QX in their interior, because they are totally there to the left of xmid. So if I have a QX to the right of xmid, I can just get rid of all of the line segments in I left. So I'm going to continue my search recursively on the right subtree. Okay, if a QX is greater than xmid, continue on the right subtree. Yeah, I guess so too. So the notification panel had the image. Yeah, it says save to clipboard. Yeah, I can also get it here. Thanks, Dennis, for that. But I don't know why the clipboard was not pasted over there. Anyway, I can also draw on this. That's good. I don't need GIMP just to show you, for example, where QX is. Yeah. Yeah, I can copy it again here by selecting and yeah, or I can just save it and open it here. So anyway, so let me try to draw here. So imagine we have a qx that is here. Okay, so if this is qx, what happens is that I'm going to continue my search on the right subtree. Okay, although the set in the right may not intersect this, it will not be reported, but I will go to the all the way to the leaf level. But what happens is that now the question we need to still solve is that what do I do with the segments in IMID? Okay, look at I have 3 segments in IMID, and I have QX. Now the sub problem that I need to solve when I'm traversing the tree, even if I go left or right, it doesn't matter. I have this problem. I have QX and I have some segments in IMID. And I have this sub problem which tells that now, given a bunch of intervals, find the ones that intersect with QX, right? For example, from this IMID, I shouldn't report this segment at the bottom, but these 2 segments at the top should be reported. Now, the problem is we have a bunch of intervals and we have a query, report the ones that intersect with it. It seems like it's exactly the same problem that we tried to solve from the beginning, right? So how does this IMID can be processed faster? Or I want to process, my overall goal is to get this entire query in log n plus k time. If my tree's height is log n, all right, I'm going to spend log n here. So when reporting this IMID, reporting to segments in IMID, I don't want to spend more than OK plus 1 time, which means that I just want to touch the line segments that I want to report. And if I touch another line segment, I just want to touch a constant number of them, which means that, for example, if IMID contain a lot of segments, you cannot check all of them against QX. You need to only report intelligently somehow, report the ones that are going to be reported, check the ones that are going to be reported. If you just check all of them against QX, you will end up with an ON algorithm. We cannot get to an O log n algorithm, right? Now, is this really the same problem? I mean, we are given a set of line segments in IMID and we have QX. I want to report the ones that contain QX, okay? It's actually a little bit different because what I know about these line segments is that I know that all of them have their beginning points to the left of XMID, all right, or on XMID. So then in this IMID, either, I mean, since they're in IMID, they start, their endpoint can be as the rightmost point that they can be, the rightmost location that their left endpoint can be is XMID. If their left endpoint is greater than XMID, they would be in iWrite, right? So they cannot be in IMID. And I also know something about QX. QX is strictly larger than XMID because I'm going to the, or larger than or equal to. It may be equal to as well. It doesn't matter. For equalities, the thing is already still in IMID. Okay, but here the problem actually is a simpler one. If you look at this line segments on the right-hand side, if I had them in a sorted list in decreasing order of their right endpoints, for example, if this is segment 1, if this is segment 2, and this is segment 3, if I have this order 2, 1, 3, all I need to do is this: go over this list one by one until QX is to the right of the endpoint. Okay, so for example, the right endpoint of 2 is to the right of QX, which means that QX this 2 should be reported, 1 should be reported, and when we come to 3, we see that 3 is less than QX, 3 is right endpoint, so we stop here. And which means that whenever we stop, if there were other line segments in IMID that were like this, I don't need to check all of them. Since they're in sorted order, I'm just going to go over them and only spend time, okay time, to report the ones that are here. And whenever I don't report a line segment, only one of them, the 3 is not reported, and I stop checking those line segments. So this actually solves the problem. This is what I'm looking for. IMIT, if I go to the right-hand side, I keep a sorted list of my line segments with respect to their right endpoints in decreasing order. What will happen if QX is to the left? I mean, if QX is to the left, I would need a different sorted list. This time it's going to be 1, 3, and 2. The order, as you can see, is different. What is this 1, 3, 2? It's their left endpoints sorted in increasing order this time, because my query will be the leftmost endpoint should for sure include QX. I mean, if QX is to the right of it. The first place where QX is to the left of this starting endpoint, the line segment is not going to contain QX, and all the other line segment that comes after this in this list is not going to contain, and none of them is going to contain QX. So therefore, our solution for an interval tree is that we recursively build trees and partition the intervals into 2. I left and I right are strictly to the left and to the right. And I mid is the set of points which contain X mid in their interior or at their beginning or end points. And for the associated structure in my tree here in IMID is 2 sorted lists. And here is an example for that in the book. 2 sorted lists, okay, which we call L left and L right. These 2 sorted lists, the L left will be if QX is going to follow the left branch when it's traversing this interval tree, we are going to use this list and go from the beginning of this list one by one, and we are going to stop at the first time we don't report a point. So we're just going to spend here on this list OK plus 1 time. And this is a sorted list which contains the segments which are sorted with respect to their left endpoints, increasing order of their left endpoints. And here are the segments which are sorted in decreasing order of their right endpoints. So this is like this interval covers from minus infinity to x mid, and this is like the interval from this is plus infinity to x mid. This is minus infinity to x mid. So it just shows which the order of the segments from minus infinity to x mid, and this one shows the same order from plus infinity to x mid. All right. So this is what an interval tree is, and what it will provide us in ON space complexity, because each interval is stored once here. It's twice actually, but in constant number of times in the tree. When we store an interval in, since we always have partitions, when we store in one of these lists, we store it twice, and it doesn't appear anywhere in the tree. So it has ON space complexity. Building this takes ON log n time. We sort the endpoints left and right, and the rest is just regular binary tree construction. And searching in this tree, this one-dimensional problem, we can search in log n plus k time, because the height of the tree is log n, and at each level of the tree we spend 1 plus k time, and this will ensure log n complexity. So we solved this version of the problem. We have our left boundary is this QX, which is an infinite line, and we have a bunch of line segments, and now we can report the ones that intersect with this QX. So this one-dimensional problem could be solved with the help of interval trees. Any questions from interval trees? So the algorithm is just very simple, just a recursive construction of these I left and I right. And for the segments in IMID, we have as the associated structure, we have L left and L right, and that's it basically. And querying is also very simple. We are going to if qx is less than xmate, we are going to continue the query recursively on the left subtree. Otherwise, we are going to continue on the right subtree. In both cases, we need to use the associated structure. When we go left, we will use this L left list of the IMID intervals. And if we go right, we use the L right list of this IMID intervals. Starting at the interval with the rightmost endpoint, we report all of the intervals that contain QX, and we stop as soon as an interval does not contain QX. That's that +1 or K +1 that we are spending. All right, so it's a fairly straightforward data structure, but it helps us solve this problem that I showed here. Now, we are going to get this problem back to its original case, which is this. This line here, QX, actually contains also two things. It's actually a line segment. The left boundary is bounded in terms of y. So it's actually spans from qy to qy prime. Now, these segments here, they shouldn't be reported. Only these two should be reported. So this is how are we going to establish this will be the next thing we are going to see. Okay, and that in that case, the query is going to turn into something like this. Let me show you how the query is going to look like. So yeah, we don't want to report this S in the middle, and it turns into a query like this. So when our query Q was infinite line like this, we were reporting everything to the left of this. Now we want to limit it between qy and qy prime. So this sorted list from -infinity to that covers to x bit, this was our sorted list. The query that we want to, in order to get back to the two-dimensional version, we want to find intervals and the left endpoints. When we go to the left subtree in our query, remember we only have the segments sorted with respect to their left endpoints, right? Because all of their right endpoints are to the right of xmit, so we don't actually consider them. They're going to be for sure contained in this Q, not in terms of their y coordinates, but in terms of x coordinates. So we were looking for a query that was like from -infinity to qx. This was what this L left was used. That associated structure we have for IMID, it was actually performing this query. All the intervals from -infinity starting with the smallest left endpoint all the way to qx, we were reporting them one by one. This was that sorted list helping us to solve this part of the problem. Now, in order to extend it the original 2D version, we need to also have this qy prime taken into account. And if you look at this query, it becomes like a 2D range query actually, because we're just now looking for left endpoints. By the way, these are this is like the left boundary of our bounding box. These are actually points that are outside the bounding box. All right. If you again think about the first original problem, our goal was to find line segments that intersect with the orthogonal query window. This shaded part is not inside the query window. If it was inside the query window, these segments would have been identified by range queries already, right? So this is actually the left boundary of the orthogonal query window. Orthogonal query window is something like this. But still, we were trying to look for, in the sub problem, we are looking for line segment that cross the left boundary. So we are going to report this one. Actually, it may be the case that, for example, if it was like this, it will still be identified because its endpoint is inside. So it may be a query window that is like this, like long rectangle. So, but this is just, since we are focusing on the sub-problem, we don't need to visualize the original problem here. Now, but what happens is that this L left does not work for us anymore because the L left contains these points as sorted. So the first segment is this, second, third, fourth, fifth, sixth, and seventh. So they are ordered like this. And this order, as you can see, the first one, second one is reported, third one is not reported, fourth one is reported, fifth one is not reported, sixth one is, so we cannot just go over all of the left elements. So this sorted list does not help us anymore. But instead of that sorted list, we build a 2D range tree for the left endpoints. This query that we have can be can be queried on this 2D range tree of these endpoints to find the ones that are inside this query window. So this becomes our query window, the segments that we want to report. And it can, as you can see, it becomes a range query, 2D range query, right? Just for the left endpoints, use a 2D range query, build a 2D range tree on them, and perform this 2D range query in log n time with the help of fractional cascading. So that actually solves the original horizontal vertical line simplified problem. The 2D version problem can be solved by replacing the associated structures of L left and L right. So here is the solution. Sorry, let me get back to the selection. So this L left and L right could be replaced by 2D range trees built on the left endpoints and another 2D range tree built on the right endpoints. Okay, so I'm going to have two 2D range trees as the associated structures, and I'm going to make this query to report the ones that are intersected, that intersect this left boundary. I'm going to perform this query, and I will be able to do it in log n time, which will at the end give me an all log square n plus k time algorithm. So the associated structures now are converted from lists, sorted lists, to 2D range trees to extend the problem from 1D to the 2D version. Okay, so that's actually what is written here. Yeah, right here. This paragraph is telling exactly what I just told. Okay, so the main structure will be the one-dimensional interval tree will be just the x intervals. Instead of the sorted lists L left and L right, now we have two range trees, 2D range trees, a range tree on the left endpoints and another one on the right endpoints. Since also the storage requirements of range trees are log n larger than for sorted lists, so our sorted lists were their space complexity were O(n), but if you use a range tree, it will be O(n) log n, so the total storage for this new extended interval tree will be O(n) log n. So this is the final outcome of this first part of today's lecture, which with O(n) log n storage, and the structure can be in O(n) log n time, we can query whether these horizontal line segments are intersecting our query window in log square n plus k time. Now, the second part of today's lecture, we are going to actually make use of this interesting structure of this query window. This doesn't look like your regular 2D range query window, right? Because it's not bounded on the left. Okay, in regular range trees, we have from regular range queries, we have a query window which is from qx to qx prime and qy to qy prime. Now, if we have these two ranges, we need a 2D range tree or KD tree. But this is like a different type of a query. We want points that are between two things in terms of y coordinate, but are smaller than they have. That are not bounded on the left-hand side. So, can we use a different structure to solve queries of this type? And this is what we are going to do in the second part. And the main goal of this second part is to reduce the storage requirement of O(n) log n to O(n). All right, we are using a different associated structure. Instead of using range trees for the associated structure, we are going to use a different tree which is going to reduce the O(n) log n storage to O(n). We are going to build a tree which is of linear complexity, but the search time and construction time are going to remain the same. All right, so I repeat, the entire part of this section 10.2 is to reduce the O(n) log n storage to O(n), and we'll be able to do that with the help of this observation. Our query is actually an interesting query, which is like print the elements in sorted order. So this is like from minimum to largest, so from minimum to certain number. For example, if you have a sorted list, this is how we use this L-left, right? We have a sorted list, we report the top k minimum elements in that sorted list until we come to a threshold, qx. So this is an interesting type of range query. And the other is a regular range. So if we have something like this, we are going to make use of two data structures and combine them together. The heap data structure, for example, for L-left, the entire L-left list could be actually stored in a heap, in a min heap. Heaps are good to query to get the minimum from a list, and actually in OK time in heaps you can get the first k elements if you have a heap actually in log k plus, or there's actually, you can throw, if you don't want to delete them from the heap, you can actually walk on the heap in OK time to get the top k elements. All right, so actually this is interesting. It means that we can sort in linear time. No, yeah, we should rearrange the heap. Actually, we can in order to report certain elements that are less than a number. It's not the top k, but if we have a threshold, for example, we can report the elements in a heap in O1 plus k time. So this is what we want to achieve. So in other words, for example, look at this heap. A min heap has the minimum number at root node. For example, if you want to say that report all the elements in this heap less than k, okay, less than 6, for example, what I'm going to do, I'm going to compare 1 with 6. 1 is smaller, report, and continue with left and right child at the same time. If for example, this was larger than what I'm trying to report, I will stop that query at that point. For example, we want to report everything that is less than 6, right? When we come to 8, since 8 is the smallest one of this subtree and it's larger than 6, I stop my printing out reporting at this point. And when we come to the left subtree, 3 is less than 6, report it, and then go to its left and right child. Touch 11, say is 11 less than 6? No, stop reporting at this point and stop the entire left subtree. Do not touch them at all. And then 4 is less than 6, report it. So we can actually report 1, 3, 4, and 8. But the interesting thing is that, yeah, it's not there. They're not necessarily in sorted order. So that explains why we don't have a linear sorting algorithm. When we report these points, also we are not interested. For example, if you just want to report them, report everything that are less than 6. When you say that in the reporting order, you're not interested whether these elements are sorted or not. All right. All you care about, I mean, you can report, your report should contain something like 431 or 341. All of them are less than 6. So when your goal is to report elements less than some threshold, you can do that in O1 plus k time in a heap. But the reported elements are not necessarily in sorted order. All right, that's a very nice property of a heap, actually. Which also shows you that if you have this threshold, you can do threshold queries in linear time. I mean, not linear time, in O1 plus k time, whatever your reported elements are. So that's really a good property of heaps. Now, before we go into the break, I just want to show you that. So heaps are good for this type of sorted queries from -infinity to qx. Now we also have the y coordinate limit, which is from y to y prime. We have two-dimensional points actually. This is a one-dimensional heap. When we have 2D points and we want to do also binary search on this, how are we going to perform such queries is a question, and we are going to combine the heap with the binary search tree structure, because heaps give us a degree of freedom. Heaps have a flexibility, which is, okay, you're going to put the minimum. The non-flexibility part is, in a min heap, the minimum elements should appear at the root node. But how the remaining two sets of nodes are divided into left and right subtrees is completely arbitrary in heaps. Okay, why is this 15 on the right hand side? It could be on the left subtree too. 11 could be on the right subtree. So the way the left and right subtrees are constructed are totally irrelevant in heaps. Okay, we just want a complete tree, which if we have an array-based implementation, all we care is the heap property. Whether they appear on the left subtree, right subtree, we don't care about those in heaps. Now, can we use this additional degree of freedom in heaps to actually decide which node goes to left, which node goes to right by using a second attribute, like the y coordinate? So this is what priority search trees are. They are a combination of heaps and binary search trees in which the division of the partitioning of the nodes to left and right subtrees are done with respect to a second attribute. And therefore, this is going to remove any degree of freedom we have. We will always have a unique tree if we have a strategy to build to partition these into two subsets based on some second attribute. This will, at each step, our tree is going to be deterministically uniquely defined, and we are going to build a tree like this. Okay, so now let's have a 13-minute break. I'm going to stop the meeting, and we are going to meet again at 10:50. Okay, 13 minutes from now at 10:50, we are going to continue with this priority search trees and solve the first problem by reducing the space complexity to O(n). And after that, we are going to now go back to the non-simple problem of arbitrarily oriented line segments. And for that, we are going to see segment trees. All right. See you all in 12 minutes. Let me stop the recording.